Today we're going to continue with our statistical model for simple linear regression. We typically want to start our regression with a graphical display. We want to determine if a linear fit is actually appropriate. So we'll create our scatter plot. We'll look at the pattern of the data. And when we design our statistical model, we have two parts to it. We have the population regression line, which is the model itself, and then there's also variation. Remember, we have points that do not fall on the regression line. Some are going to be above and some are going to be below. So now that we're moving towards inference, we're going to look at an equation that has both parts, the model itself and the variation. So we use data equals fit plus residual. So if we use this model, the fit portion is what we're used to seeing. It's our slope and our intercept and whatever observation or subpopulation we're using. The residual represents our variation from the line. So these are deviations that we know are either above or below. Even though we think of deviations as not being normal, the deviations actually are normal because the line has been fitted to what we've observed. So the deviations themselves are classified as having a normal distribution. So the residual is going to be represented by the lowercase Greek letter epsilon. So again, the residuals are the variation from the line. Sometimes the book will call it noise, but anything that fits specifically on the line is going to be classified as a mean, and then anything above or below will be a deviation from that. If we had a perfectly straight line, that means that every point would line up. We would have a correlation of 1, and there would be no variation, which is not practical. Once you design an inference model for simple linear regression, we can use it to make predictions. So you can make predictions for your subpopulations as a whole, but also just simple values of X that you don't see in the model. So with simple linear regression, we examine n observations of our explanatory variable, and then we look at the response along the y. We typically gather this information in sets of ordered pairs, and you can have as many as you like. Usually the sample size being larger will be better. So we're looking at the observed response value of y when your explanatory variable takes on any value of x. Remember, we want to only use what's on the graph. We don't want to go beyond the scope of the graph too far. Otherwise, we're extrapolating, and potentially we could be wrong in our prediction. So this is really the simple linear regression model. So we have our predicted value of y. We have beta sub 0, which is going to be our intercept. Beta sub 1, which is the slope for the model. The observed value, x sub I. And then, of course, there's variation. We're not really going to see the variation in the model. We're going to stick with our normal y equals mx plus b. But the parameters now that we're working with an inference model are beta 0, beta 1, and then we are going to use a standard deviation in this model. When we're using the inference model, remember we're using means for different values of x, which should be more accurate in predicting our value of y. So we're using the prediction of mu sub y. So the slope and the intercept are going to help us determine that final value. So these are our parameters. Remember, again, we don't want to extrapolate beyond the scope of the graph for fear of making a mistake. So typically we want to predict y hat. We're now going to convert that to mu of y, and this will be our unbiased estimator. Our slope b sub 1 is now going to be beta 1. B sub 0 is now beta 0, and again, they both represent the slope and the intercept that we were used to in our earlier model in chapter 2. And then we have our residual for our deviations from the least squared regression line. In earlier chapters, we did calculate the residual, which was the deviation from the least squared regression line. So that is the same calculation. We want to do observed minus predicted. When we look at the deviations, if we're going to calculate standard deviation by hand, we know that the simple deviations that we've calculated for E sub I should sum to 0. The same thing is true for epsilon. Even though we're working with means, the deviations should sum to 0. So we're going to look at standard deviation, which is going to measure our variation about the least squared regression line. And we'll have a formula that will help us in estimating that. So S will be our variance. We're going to use the sum of the squared deviations, and then we're going to divide it by n minus 2, and that's basically your degrees of freedom. So again, the deviations will not be present in the model, even though we saw that on the last slide. Just know that the deviations are there. You're going to check those by making a residual plot and then looking for that scattered pattern in your residuals, and that will confirm that we've met the assumptions to use a regression line. Syracuse typically uses a Minitab output for most of their data. So we just want to learn to look at this and analyze it. You can see at the top that they're looking at the IQ of a child versus the cry count that they've recorded. I don't know if we talked about this example, but they snapped a rubber band on the baby's heel to see how many like sobs it could get. So along the top, the predictor, we have the constant. This is beta 0. And cry count, which is going to be our slope. So the coefficient is the number that we're going to use in the least squared regression line. So beta 0 will be 91.268, and beta 1 will be 1.4929. We will get to these other values soon, but you can see there's p-values listed here. So when we run our inference test, we're looking at the slope, and my slope p-value is less than 0.05. So in this model, we would have evidence against our null. But what we want to do is write the least squared regression line for this particular analysis. So what we're trying to do is predict the IQ of the child. So we're going to use the coefficient from cry count, 1.4929. Cry count is x, and then we have our slope of 91.268. So from this Minitab output, you could write the least squares regression line, and then you could move further and make predictions. We want to make sure that we check the assumptions before we use our least squares regression model. So one of the assumptions that we can check is that the residuals are normal. So we can make a residual plot. The scatter plot has to be created first. And just to make sure, we should also look at a normal quantile plot to look at the data. So the residual plot will look scattered. The quantile plot will be fairly straight lined. If both of those assumptions are met, then it looks like it will be safe to use our model. So truthfully, you're going to check one by one, but it really does come down to those residual and quantile plots. But when we make the scatter plot, we want to look at it and is a linear relationship appropriate? If you do see some kind of linear relationship, we can move on to our next assumption, that our response variable is normal for our population of interest. Are all of my observations independent? Typically, this is just assumed and we know that they are. Now, if you think about the graph a few slides back where we had the different curves coming up with the inference model, we could see that we were connecting the means for each subpopulation. It's also assumed that those standard deviations are the same for each subpopulation. So the graphical model will give you the best way to check that the assumptions are met. So residuals are scattered and the normal quantile plot looks like a straight line. We can safely assume that a linear regression model is appropriate. All right, that's the end of that lesson. This will be homework 10.32. You're not going to do part C, but I have put it here, and I will make sure that I send the data to you. If you have any questions when you're going through the homework or working on the packet, please make sure you contact me, and I'll be happy to help. Have a great day.